Okay, good. All right. So again, this one's recorded because sort of several people cannot be here today. But let's try this. So if I start recording and nobody shows up again, then definitely no more record. Okay. So this sort of one-time thing to accommodate sort of a large number of students who cannot be here. So before we continue going with optimization and economic dispatch in this lecture, any questions from the homework? Any issues, any question about homework? So again, for the homework, ask you, some questions do not solve by hand. So just use whatever computer program you want. Okay. I don't particularly care how you get a solution. If you insist on doing that by hand, sure. But later we'll look at linear system that's for 20 by 20. Right? So the idea is you need to be able to solve system equations, okay, in some way. All right. So the system equations come up because in power systems, really the way system works is you solve a optimization problem with many variables, right? So last time we saw something like minimize x, subject, right? So f of x. So here when I write x, almost always assume x is a vector. Okay, so f is a function that goes from Rn to R. Okay, so the output of the function is a scalar, but does take many variables into account, right? So for example, we could have so x1 minus phi squared plus x2 plus 3 squared plus x1, x2. Okay, so something like this. It's a perfectly okay f. So we're going to minimize. Well, minimize meaning find the value of x1, x2 such that the function of such that f takes the value of f is small as possible, right? So last time we saw is a necessary condition is that the gradient of f, basically this is a partial derivative, right? So if you're at a local minimum or local maximum, then the gradient basically has to be equal to 0. Right? So if you take a partial derivative, this is called the gradient of f. And if you are at a minimum, then this gradient has to be equal to 0. So this is called a necessary condition. Right? So this has to happen at a minimum. So why this necessary? Can you remember any intuitive explanation on why this is necessary condition? Good, right? So if you think about, again, the Taylor expansion, what you get is you get a linear term of the gradient multiplied by the changes in x. So if this is non-zero, you can always find a direction of change that makes the value smaller, right? So this is necessary. This is not sufficient, right, for most problems, because one, you don't know whether it's a mean or max. This actually happens quite often. So, people, if you look at, any of you have done any machine learning or trained deep neural networks or any of that, you almost never know like what you get. You train until gradient 0, but you actually don't know which one you are. So a condition for you are actually at a minimum, right? So x star is a local mean if the Hessian, so this is h, these are now the second derivatives, is positive, definite. So this means that the eigenvalues of h are all greater than 0. Okay, so this is local mean. If this happens, it's a local max if all the eigenvalues are negative. Okay, so again, because this is a symmetric matrix, the eigenvalues are all real numbers. So you can talk about either positive, either negative, right? So a local max if the eigenvalues of H less than 0, right? All the eigenvalues are less than 0. So what happens if your eigenvalues are mixed? What is the interpretation, right? So you can have a, let's say, 5 by 5 matrix. Then let's say 2 of them are positive, 3 of them are negative, or something like that. Then what is going on there? Right? You get something called a saddle point. What a saddle point is a fancy name for basically saying the following. So what does H do, right? So H tells you the sort of concavity or convexity of the function. Each eigenvalue basically tell you about the convexity in one direction. Okay, so imagine you have a three-dimensional thing, right? So you want to know is concave, convex in this direction, convex in this direction. So if they're all positive, that means it's convex in every direction. If it's all negative, it's concave in every direction. If it's mixed, it's convex in some direction, concave in some other direction, and you make no claim, right? So just you don't, then that means you get stuck. Right? You did not reach a minimum. There's not a minimum or a maximum, but the solver stopped because the solver solves basically by looking at when this is 0. Okay, so the solver solves by trying to make this function 0, the gradient 0. Then you can check whether you actually got a local minimum. Okay. So much of the sort of modern optimization theory is to deal with the fact that when do you have a mixed eigenvalue? So if you're at a saddle point, what do you do at a saddle point? For us in power system economics, in markets, we'll never sort of reach that issue because later we'll see that we'll design the optimization problem to not have saddle points. We'll design the optimization problem to be always that, this will be a necessary and sufficient condition. So that's a choice we'll make. Right? So you look at for example, if you bid into PJM, you bid into that market, a lot of the requirement is such that the PJM computers can solve the optimization problem. Okay, a lot of requirement is not really physical based. As my computer needs to be able to solve this thing in 5 minutes. I need to terminate in 5 minutes. So you have to submit this kind of bid. Right? So I don't care what your physical characteristics are. Bid like this, so I can solve. We'll later see what are those sort of technical requirements. But for general optimization problems, this could happen, saddle point could happen. For process economics, mostly is this necessary condition will imply the sufficient condition by choice, by design. Okay. So this is a sort of viewpoint of a unconstrained optimization. The reason this is called unconstrained optimization is because X can take any value you want. So X can take whatever value you want. So X is free to be between minus infinity to plus infinity. But obviously that's really not what happens in practice, right? So most times in practice, what you care, you're limited, right? You have to deal with the fact that you have to operate in a feasible set. Okay? So feasible set is describing the fact that your variables can only exist within a limited range. So if you talk about generation, you have to, let's say, between 200 and 500 megawatts. Right? So you're optimizing something, but your X is limited between some range. So active power is limited, reactive power is limited. If you ever sort of optimizing something, the physical dimension of let's say you buy a new transformer, transformer has to have a positive size, right? All this constraint optimization. Okay. So often it's not, so if the problem is unconstrained, we know how to solve this problem, at least for differentiable F. It's algorithmically not too challenging to solve this problem. Constraints are sometimes difficult to deal with, and often sort of understanding constraints is how you understand the optimization problem. Okay? And the reason I put for transformer here is, so do not discount the fact that transformer has a certain size. So for the UW campus, do you know where our transformer is? Does anybody know? Right. So as a campus, we get some power. That power comes out of transformer. Anybody know where that transformer is? Not in this C building. You don't want to be anywhere close to the transformer. So under I5, that's a substation. That's where supply power to the entire area. Then the campus has its own transformer. This is close by the police station, actually, on 15th, I think. So you could drive down by 15th, or next to the police station, you see a white building, unmarked white building. That's where the transformer is. And the huge problem for our campus is we cannot put in a larger transformer. We're limited physically by the size of land there. So if we want to increase the load in the campus, we need a bigger transformer. We can't put in a bigger transformer because that's all the land we have to put in a transformer. So that's sort of a lot of interesting constraint that comes out of that problem. So it's actually a very sort of complex optimization problem. If you build a new building on campus, what do you do? There's a lot of optimization there, constrained by the fact that the transformer has to be a limited size, right? So feasible size does matter. And as you go on, you solve sort of hard optimization problems, for almost always a feasible set that makes things hard. And almost never the objective function. Almost always feasible set is a harder thing to deal with. But the idea is if you look at this kind of optimization problem, right, so you have a feasible set, that means that you only care, let's say finding the maximum, you only care about this maximum, right? You only care about the function values within your feasible set between x min, x max. You don't care about the other point, which is higher, but it's outside your feasible set. Right? So we have a feasibility constraint. That means this is the only part you care about for this problem. Okay? So you can look at this sort of in higher dimensions, right? So this is a drawing sort of geometrically in two-dimensional case, right? So this is a convex problem. At this point, you have the first order optimality condition. So the gradient is 0. This is flat down there. Then the second order condition is that this is convex thing opening up, right? So you know this is minimal. Okay. So this is just drawing some picture for us. And this is the saddle point condition. So what happens if some of your eigenvalues are positive, some are negative? This is you're decreasing along this dimension. You're increasing along this dimension. So you get stuck at this point. There's neither a minimum or a maximum, but your solver can tell. Okay? Your solver is not very good at telling this. Okay, so get stuck at that point. This kind of point is, so again, this doesn't happen really in power systems, but in many other optimization problems, you will get stuck at saddle points. And a lot of algorithms are how to get out of this point and so on, but this is something that can happen. So the sufficient condition is you compute the Hessian, and then you sort of, right, you look at the eigenvalues of the Hessian and so on. Okay. Okay, so you can compute the eigenvalues Hessian. Okay, so one thing you have to keep in mind is it easy or hard to compute eigenvalue of a large matrix? Is it an easy problem? Is it a hard problem? Is it very costly? Right? How long would you take to compute eigenvalues of a large matrix? Is that fast or is that slow? Okay, so it's actually quite slow to compute eigenvalues of a large matrix. It's not incredibly fast. Eigenvalues are not trivial computations. Okay, so one reason that we don't check the Hessian a lot of times is you don't want to do this eigenvalue computation. This scales poorly. Okay, so as your number of variables grows and grows, becomes very hard to compute the Hessian of a matrix. Okay, right? So for example, so if you think about, let's say, again, so the largest market we have in US is PJM. This thing can run easily into, if you include demand response and small generators, you can have generators. Okay. You can have this, so each one of these is your variable. Okay, so you basically have 20,000 variables. You're trying to optimize something, figure out how much each of them generate. Then what is the size of your hashing? Right, so 20,000 squared. So how many elements do I have in the hashing actually? Right, so your H, this thing is, right, so this is about 4 times 10 to the 8. So close to 500 million parameters. You really don't want to compute all the eigenvalues of this thing, okay? There's way too many eigenvalues for this to compute. You're not going to compute this within any accuracy, okay? So eigenvalues is something you can check for small problems, but for larger problems, may not be the sort of best thing to check. Okay? All right, so I'm going to assume you know how to compute eigenvalues. So we're going to skip all this eigenvalue computation, but again, remember that for these sort of examples in class, you can do it. For larger problems, not the great idea. Compute eigenvalues, okay? So let's do one example to see how it uses. So let's say minimize x1 squared plus 4x2 squared. Okay, so let's say we want to minimize this problem. So you take a first order, you take the partial derivative, respect x1, you get 2x1 minus 2x2, right? You take a partial derivative with respect to x2, you get minus 2x1 plus 8x2. You set both to 0 and you solve this system equation. Any questions here? Okay, just sort of go and take partial derivatives. One thing to remember is make sure you do this sort of carefully. In the finals, this kind of problem, people tend to do it very fast. And it's very easy to mix up when do you have x2, when do you have x1. Right. So it's actually not that hard, but just carefully take the partial derivatives and solve this system of equations. Turns out here that you get x1 star equals to 0, x2 star equals to 0. So 0, 0 turns out to solve this problem. And then next, you want to check the Hessian. Okay. So the Hessian here, this is 1 squared. You plug things in, this is 2 minus 2 minus 2, 8. And you can compute the eigenvalues. Turns out that the eigenvalues are both greater than 0. Okay. So you can conclude that so the point you got is a minimum. Questions for this? So it's very sort of mechanical procedure you can apply here. Right? So you take partial derivative, you get a system equations, you evaluate the Hessian, then you're done. Okay. And again, in this class, vast majority of the time we'll be using quadratic cost. With the nice thing being that you take one derivative, you get some linear equations. You take a second derivative, all you have is constant coefficient. You can find the eigenvalues. Okay, so the numbers will be picked so that the problem is particularly nice for you. All right, so this is one example in this example, right? So basically, if you look at the function as that's your minimum, and then function grows as x1, x2 grows larger and larger. Right? So this is a picture of the function. So let's do one more example to see a saddle point. So this is what happens when you see a saddle point? So this just flips the sign on x1 squared. So you can do the derivative. You can this still gives x1 star equal to 0, x2 star equal to 0. So if you do the derivative, you still get that the first order stationarity condition, the first order optimality condition tells you that x1 star, x2 star should both be 0. Now you can compute the Hessian for this problem. The Hessian you get is -2, 2, 6. Okay? You get this Hessian, and here the eigenvalues are 4 plus square root of 80 over 2. This is bigger than 0. 4 minus square root of 80 over 2. This is less than 5. Okay. So this is an example where the necessary condition is true, right? Both x1 star, x2 star equals 0 solves the problem. But if you check the second order, the eigenvalue of the Hessian, one's positive, one's negative. Okay, so this is not a minimum, nor is it a maximum. What happens is at 0, basically you have one function that's getting smaller as it approach 0. You have one function that's getting bigger as it approach 0. So this is called a saddle point. You have a saddle point at 0, right? So if you go along this direction, you're getting bigger. You want to be at 0, but you go along this direction, you're actually getting smaller. Okay? So here you have a saddle point. So all this may happen. Okay, any questions for these two examples? All right, so in practice, of course, we don't check Hessians. In practice, you almost never check Hessians. What you do in practice is you want to guarantee the problem is convex, and the solution you get will be a minimum, okay, without checking Hessian. What you want to do is you want to guarantee this. Okay? And the way we guarantee this is basically you want the function you're trying to minimize have some properties, have some sort of nice properties that it should have. Then what you can guarantee is the function will always be a minimum. So for us, we often optimize function of the following form. Okay. Right. So for us, what we tend to minimize is this type of functions. And the interpretation is each I is a generator. This is your cost function for a generator. And you sum them all up, you want to minimize the total cost of something. So for this type of equations, if you evaluate the Hessian, what do you get? Let's say you're trying to minimize this thing and evaluate the Hessian. Right? So this is particularly easy because if you evaluate it, you take two derivatives. There's no cross terms in this problem. Right? For us, each generator is independent. They all have their own cost function. They don't have something like x1 times x2. So the Hessian is 2a1, 2a2, da da da, 0, 0, right? So you have this kind of Hessians. For this kind of Hessians, then this is positive. So the eigenvalue basically are just these numbers for a diagonal matrix, right? So the eigenvalue of a diagonal matrix are just diagonal entries on the matrix. So this thing is positive definite if and only if these numbers are all positive. The numbers are positive, then the Hessian will be positive definite, and you can when you minimize, you'll get a local minimum point. So what happens in practice is when you bid, you're required, your AI has to be positive. Right? Doesn't matter where your generation curve is. You need to put in a positive AI. Okay? If you want to be in the market, you're required to put in a positive number at the entry. Otherwise, the market wouldn't clear you. Okay? So is it that would every generator have this form? No. some generator, there may be a operating point that's sort of more optimal than others. The function may be, sort of increasing then decreasing or then increasing, something like that. But all of that is not allowed in the market. In the market operator insists this is the form you put in to, right? And the reason is we need to be able to solve the optimization problem. Okay, so power system economics turns out to be often a trade-off between what is sort of realistically true with what is computationally possible. And often as we do the computational possible thing. Okay, so whenever a question between should I be more realistic or should I be easier to compute, we often choose that we should be easier to compute. Okay, we need to calculate something. So we can relax how realistic we are. Okay. So if you read a book, you see the generation costs are quadratic and convex. There's some physical sort of feature. There's some sort of physical reason behind that, but also the reason is I just want this hash to be positive definite. So I know when I solve the problem, I'm at a minimum. Okay, so you have to. This sort of cost we'll deal with. Okay. All right. Any questions about this? Yeah. So what they do is you don't submit A, B, and C. You have to make this into a piecewise linear form. So what you do is you have your A, B, and C, then you submit a piecewise linearized version of that. The reason being that a quadratic is too hard. I want to solve a linear program. So you're forced to submit a linear, sort of piecewise linear bit in that form. But you can think of they're forced to submit this. It's sort of good enough to think about. They're forced to submit. Yeah. Okay. Any other questions? Okay, so now we're getting to the fun part. The fun part is what happens when we have constraints, right? So for power systems, we typically always have constraints, right? So you remember the motivating example is I have some load, some generator A, generator B, and them to satisfy the load. Right? So the optimization problem is minimize the cost of generator A plus the cost of generator B, subject to the power you get equal to this load. Okay. So like this. Okay. So the idea, so that's where your constraint is, right? So constraint means, let's say the load is 10 megawatts, so my total generation has to be 10 megawatts. Then your choice is who generates how much in this type of problem, right? And this is where sort of what Neumann's idea comes in is, if you look at this problem, what do you want is, not only do you want to figure out what the optimal PA and PB is, you also want to figure out a price out of this thing, right? So that's the challenging part is, suppose I can solve this problem. What do I do with the price, right? How do I get the price to come out of this? So let's look at an example and think through this example. Let's say I'm going to minimize half x1 squared plus 2x, let's say x2 squared. Okay. Let's say I want to solve this problem. So how will you solve this problem if I just gave this to you? Let's say sort of purely I want to know the x1, x2 that minimize this function, subject to that they add up to 1. Right, so what you do is you substitute, right? So I know I have an equality condition. So what can I do? I can say, well, so x1, 1 minus x2, right? This condition tells me that. Then what do I get is I got to minimize 1/2, 1 minus x2 squared plus x2 squared, right? I got this problem. Good. I can expand this. This is mean. So this is unconstrained. So the problem like this is unconstrained. How do you solve this problem is you take derivative set it to 0. Okay, so let's take derivative set it to 0. Okay, so x2 is only variable now, so I have minus 1 minus x2 plus 2x2 equals to 0, right? This is my function. So I have 3x2 equals to 1. And x2 equals to 1/3, x1 equals to 2/3. Okay, any questions about this? Okay, you substitute, you take a derivative. Right, so again, this is a quadratic with positive coefficients. So I don't need to check the second order condition. I know sort of this is a minimum. Okay, so everything so far so good. How do I get a price on this? Let's say these are generators, and I need to pay this generator. So I know how much they should generate, but what about the price? Right? So you tell generator 1, you should do let's say 2/3 of megawatt. You tell generator 2, you should do 1/3 of megawatt. How much do you pay them? What is the price? Okay, good, right? So price is the derivative of the cost. So whose the cost should I take a derivative of? I have two generators. I have two generators. So my market needs a common price. I'm selling electricity. There's only one product. Right? So, but I have two generators. So who determines the price? Which one do I take a derivative of? So in this case, what must the answer be? Does it matter which one you take derivative of in this case? Right. So let's look at the price in this case. Okay. So let's look at the cost and the price. So the cost, right? So let's look at price as a derivative of cost, right? So let's do this for 1 and 2. Right? Let's do this for 1 and 2. So price of 1, this is the x1, 1/2 x1 squared, evaluated at x1 equals 2/3. Right? So I understand what this is doing. Right? So I have a cost of 1/2 x1 squared. I'm generating 2/3, right? So 2/3. I want to know what is my marginal price at this point. Okay? Is everybody clear with what this equation trying to do? Make sense? Okay, right? So what do you get at this point? Right? You got 2/3. Right? So half comes down, you got 2/3. How about price for 2? What is the price? What is the price if you take sort of cost of generator 2 as a cost? Right? Also 2/3. Right? Also 2/3. Okay. Any questions with the calculation? Yeah. Right. So the calculation we're trying to do is I need a marginal cost. I need a price come down. I have two cost functions. So let's just do one for price, do it for price for the first one, and do it for the second one. So it turns out the price is always happens to be equal, right? So there's only two generators, and they somehow have the same marginal cost. In this case, the price is 2/3. Okay, so it turns out the price in the system price should be 2/3 because both of them agree. Right? They both have to be 2/3. Okay. So the question now becomes: is this just luck, Or is this always true? Okay, is this just dumb luck because I picked the parameters to be nice? Or is this just luck because they happen is quadratic? Or is there some sort of deeper reason this must be true? So this is a key point behind sort of how the entire US electricity market is structured, is through this observation. So if you look at this optimization problem, okay, so let's just focus on this optimization problem. This one here. Must the marginal cost be equal to each other, x1, x2? So what happens if the marginal cost is not equal? What happens if I say at optimum, let's say x1, the marginal cost for 1 is less than the marginal cost for 2? What happens in that case? Right. So what happens in this case is, right, so I have a sum constraint. But then if one generator is cheaper than the other, I can always reduce production on the more expensive one, increase production on the cheaper one. Okay, I can always do that, right? So if the marginal cost is not equal, there is always a way to move where you reduce one, increase the other, such that the total cost go down. Okay? So that's the intuition behind why the marginal cost must be equal for this problem. Okay, it doesn't have to. It really doesn't have anything to do with the fact this is quadratic or the coefficient somewhere. It has to do with the fact that for a equality constraint, you're free basically to operate on a line. And then if there's any cost difference between the two generators, you can trade off one against the other to achieve a better outcome. Okay, so that's the intuition behind why the price at optimum must be equal to each other. Okay, so the idea is, so the at the optimum point, the price must be equal. Otherwise, we can trade off. Okay? So if one is more expensive than the other, you can always trade them off, right? By sort of more of one, less than the other. The only time you cannot do it is if the price is equal to each other. Okay? Any questions about the intuition behind this observation? Go. No, this still works. It doesn't matter. You fix the other one, right? So then your derivative becomes a little bit more complicated. But still, this sort of observation holds. As everything, right? So what happens is there must be one price. Otherwise, there's always a case you can do is increase a little bit more than the other one, decrease a little bit of the x1, increase x1 a little bit, decrease x2 a little bit. Okay, so if the marginal cost is ever different, you can always do this trick. Okay, so that depends on the marginal cost. But the marginal cost, if the marginal cost is different, then you can always do this. Right? So you can always decrease one, increase the other. Okay, so you're looking at the partial derivatives. If the partial derivatives are not equal to each other at the optimum point, right? So think again, even their cross terms, you can extend this into Taylor expansion. Right? You have a linear term that's partial derivative times something. So the partial derivative is not the same. Then there's always some direction I can go to make the entire function value smaller. Any other questions about this? Okay, so this is fairly easy to prove if everything's quadratic and you only have two producers. You substitute one to the other. You can easily prove that the marginal cost must be equal to each other. What is harder to prove is what happens if you have more than two, right? So substitution is harder to do. And to show that mathematically, this is always true. And that's the idea of duality theory. Okay, so this is sort of duality theory is basically showing that this is always true. It provides you sort of necessary and sufficient conditions when a constrained optimization problem is at optimum. That's what duality tries to do. This gives so duality theory says you really should not think of a constraint optimization problem as sort of substituting one variable for other variables. We should think about as you introduce some new variables to turn into an unconstrained problem. Then you can draw conclusions based on the new variables you include. Okay? Right, so let's take a break now. Then sort of take a 5-minute break. After I come back, we'll look at sort of the math behind this. And the math we cover will be infinitely simpler than the math you would do, let's say, in an analysis class. So this really extends to very, very deep sort of mathematical fields of duality theory. What we will do a very simplified version of it, which is sufficient for this class. Okay, so let's take our break, then we'll look at how the math works out. Yeah, sure. Yeah, sure. Oh, this is AI. Oh, sorry, yeah, sorry. No, no. Square the wrong thing. Yeah, square the wrong thing. Yeah, good, thanks. So what is equality constraint? It's conventional to write equality constraint as something something equal to zero, something something equal to zero. Okay. So for example, if we have a load constraint that's x1 plus x2 equal to L, we'll write this L minus x1 minus x2 equal to zero. Okay. So for simplicity, we just say we have all zeros on the right hand side. This is a convention. Doesn't mean it has to be. Right? So if let's say x1 plus x2 is a constant, this is the form we will have. What we do is we write it as something equal to zero for the constraint. Okay? So one thing to keep in mind is how many constraints can you have in this kind of optimization problem. Okay, so you don't want to over constrain your problem. The meaning of over constraint problem is, let's say you have n variables and m constraints. How large can m be? Right? So the largest m can be is equal to n, turns out. Right? Otherwise, right? So if larger than n, there's normally no solution. Okay, so things to remember is you have more constraints than variables. You normally can't solve this. You can't satisfy. If you have 2 variable 3 equations, and can't satisfy 3 equations at the same time. Okay. So this actually you need to check. Often in power, what you have is that first go around, you have m larger than n. You do anything practical. Okay, you talk to sales light, you ask the policy people what you want. They give you like 2,000 constraints where you have like 100 variables. Okay, so this happens more often than you think. So you have to explain to them, look, I can't solve your problem. This conversation we normally have. There's just no way we can solve the problem. Right? It's not us as you have to give me a possible problem to solve. So if n equals to n, there's normally sort of one solution. Right? It's just you're not optimizing anything, but at least normally there's some feasible solution you get. And then if m is less than n, this is an optimization problem. Okay, so when we say we're solving optimization problem, I need to have some freedom to move my variables around. Right? So normally you have a lot less constraints than the number of variables to do. But again, this is or doesn't always happen in practice. Okay? So this is what we want to do. And then so now we'll draw some pictures of what can happen, right? So Let's say again, so minimizing f, this is 0.25 x1 squared plus x2 squared. So this is subject to, right? So the s dot t dot is subject to. That's 2, this constraint being, let's say, 5 minus x1 minus x2. Okay, so geometrically, what does this thing look like? Well, so it's a constraint. So your x1, x2 has to satisfy this equation. So what does this equation give you? It says, okay, so basically, this is your equation. And what you can do is you want to move along this line to find the minimum point, right? So this constraint tells you have to be on this line, and you move x1, x2 along this line to figure out what minimizes cost, minimizes objective function, right? Okay, so you can solve it in various ways. Let's say you figure out this is your minimum. Right? But geometrically, constraints means that instead of optimizing over a sort of two-dimensional space, now you're optimizing over a one-dimensional space. Right? The constraint being a sort of lower dimensional space. Right? Okay. So this is sort of the geometry of the picture. And this is what almost always happens for us in power system, as we'll have load, generator, G1, G2, and A1 plus B1x. Right, so we have this for generator, and you're minimizing the cost of one plus the cost of the second one, subject to x1 plus x2 equals to f. Okay. Right, so you can't. What we have seen before is you can do this by substitution. Right? So we could substitute x1 equals to L minus x2, solve the unconstrained problem. There's certainly something you can do. Okay? Well, the drawback being that this doesn't tell you anything. Right? This is one that you have no sort of insight. Right? It's very mechanical procedure. This is, for example, how your computer may go about solving this. But for us, there's no insight. Right? So why did the solution come out to be the way it is? Another big problem, this is impossible if this constraint is not linear. Okay? It's very impossible. I don't know how to substitute. Let's say your constraint is x1 squared plus x2 squared equals to f. Then there's a much harder substitution problem in that sense. Okay. So we don't typically encounter this too much in power. The sort of most constraints are linear. It would be like power generation plus first generator plus second generator equals to a load. So for power systems, one might just not be linear. Think of a case where you sum up the power. It's actually sort of nonlinear. You have a nonlinear constraint on the power equal to load. Can you think of these cases? Not necessarily x1 squared, but sometimes when it's not x1 plus x2 equals to L, could this happen in power? So this does happen in power system where there's losses on the line. So what typically happens in power is you have a transmission line, you're sending power. Not everything makes it through, right? So there's resistant heat. There's some part of turns into heat. So this is sort of nonlinear dependence. So sort of the more power you send, the more that gets lost along the line. So normally it's not x1 plus x2 equals to L, it's sort of some function that accounts for the loss equal to L. That gets very complicated, right? So like in my PhD, basically one problem I worked on is how to account for those losses. But the losses typically are not that big. So good losses in power system in transmission line is about 1% at most. the voltage is high enough, our loss is very small. Okay, so losses does not occur in the transmission system, basically. So for us, it's most linear, right? So for our problem, if you really want it, you could do it by substitution. It's just that I need a price to get out. Okay, so the price is, what you do is you do something called Lagrangian multipliers. Okay, so again, this is the way that we want to think about it. Goes back to this. So Lagrange is the guy who discovered this or who first used this trick. The word multiplier will become clear later. This will become clear later. But the idea is, again, so this becomes an interplay of how do you modify the gradient condition. Okay, so you have a function f of x1, xn, the gradient is this is your gradient, right? So in the unconstrained case, what you do is you look for when this gradient is identically zero. In the constrained case, you cannot make this zero now, because again, in that example, you have to move on this line. There's no guarantee any point on that line the gradient is zero. Okay, so the whole thing for Lagrangian multipliers is okay. Now I need to modify the condition. I can't have gradient equal to zero anymore. So what should the gradient equal to? That's basically the idea. Is rather than checking, is this vector zero? This vector needs to be something. It cannot be zero, but still this vector needs to do something. So let's see what this vector does. Something it needs to do. Okay, so now the idea for the property of the gradient, let's say you compute a gradient, right? So let's say you compute a gradient. And it tells you that the gradient, okay, so let me draw the constraint. So imagine this is your constraint, okay? So imagine this as a linear constraint that we have. Now, so what you're doing is you're basically computing the gradient at each point, right? We can do it at each point and compute a gradient. So let's say at this point, gradient points this way. And this point, the gradient points this way. Okay, so gradient is another vector that points in various ways. Okay, so then Lagrange, or for more von Neumann, was looking at this, and now you think about this geometrically as, let's say at this point, we can evaluate the gradient pointing this way. Could this point be an optimal solution? Could it ever be an optimal solution? So this is where you geometrically think about it. Right? So if it's true, I'm constrained to move on the blue line. But is there a direction on the blue line I can move to make my functional value smaller? Which way should you move, right? You can move that. Because what happens, say, hey, what does gradient say? Gradient says, well, your function is going up in this direction. And the key thing about the gradient is I don't have to go along the gradient. As long as I'm aligned with the gradient, my functional value is increasing. Okay, so if you want to decrease the functional value, as long as you're anti-aligned with the gradient, you can decrease your functional value. That's sort of the key observation of people make. Okay? So this is the important point. So their sort of math turns out to be quite simple, but the idea is again comes from the Taylor expansion part of this function. So if you take your Taylor expansion, some x0 plus the gradient transpose for x minus x0. Okay. So what you can think of this as delta x, some direction you're moving in. So the functional value increases, right? So f is larger. Greater than zero. This doesn't mean your changing x is along the gradient. Okay, so you often hear about gradient descent, gradient ascent, all that sort of thing. This says you don't have to follow the gradient. all you have to do is make sure the angle between the two vectors is less than 90 degrees. That's all you have to do to increase the functional value of this function, right? So, okay, so this is, I don't need this to be sort of exactly sort of along the gradient. This happens if the angle, right? So it's less than 90 degrees, right? So the inner product is positive, then make a sort of acute angle, then I can increase my functional value. Smaller if I can make this angle less than that, right? So this is smaller if this product is negative, so the angle delta x is larger than 90 degrees, right? So then make a obtuse angle, then you can decrease the functional value. Okay. And that's clear. And this 2 point clear. Okay. The point is you don't have to move along the gradient. Okay. As long as you move at the angle, then this works. So before for the unconstrained case, right? So in the unconstrained case, the gradient has to be 0 is unconstrained. Right? So in the unconstrained cases, the reason I insist the gradient has to be 0 because you can go in whichever direction you want. As long as the gradient is not 0, I can find your direction you want to go. In the constrained case, this is not true. You're constraining how you can move. Okay, so instead of the gradient becoming 0, what tells you is the inner product between the two has to be 0. That's the change. Okay, so in the constrained case, this inner product has to be there. Okay, for you to be at the optimum. Right? We're no longer looking at the gradient itself. So you look at this, basically, if you look at this problem, this picture, what happens is, if the gradient points that way, can I decrease functional value? Of course, I can go in this direction. Okay? I can go in this direction, decrease functional value. I'm going anti-aligned with the gradient. My angle is more than 90 degrees. That's sufficient, right? So I can decrease the functional value. So what color should I pick? I say, go this way to decrease the functional value. What happens here is I can go this way to decrease functional value. Right? As long as I make a angle, right? So as long as the angle is not 90 degrees, you're fine. So where does the optimal happen? The optimal happens when your gradient is exactly perpendicular to your constraint. Then there's no way I can move. The inner product 0, then I'm stuck. I can conclude as an optimal point. Okay, so where does it happen is if this is at a right angle, right? If it is 90 degrees, then this is the optimal point. The reason this is the optimal point is I can't move anymore, right? So I'm constrained. Right? So I'm whatever way I move, I don't change the functional value. So this is a minimum solution, I think, in this case. Okay. Any questions for this picture? This is basically it for the, yeah. Yeah, yes. We're going to assume that the function is continuous differentiable. Okay. Always continuous differentiable. If it's not continuous, a much more difficult problem. But for us, we'll assume it's continuous. Good question. Yeah. Okay. Yeah. Any other questions for this? Okay, so this is entirely it for optimization constraint, equality constraint optimization. The idea is your condition is your dot product between the two has to be 0, right? Okay, so now your job is to algebraically write down an equation that represent a 90-degree angle. So all you need to do is translate this picture into math, into algebra. That we know how to do. You take two vectors, you multiply them, has to be 0. Okay, so that's all there is for this. But so the key thing to remember is when you're constrained to move, you want to make the dot product 0. The dot product is 0 if and only if you're perpendicular to the gradient, right? Your constraint is perpendicular to the gradient. Okay, okay, so that's the whole point that we have. So we're going to skip some examples. It's not too terribly interesting. So the way Lagrangian multiplier works is converting that geometric picture to a algebraic picture, right? Converting that to algebraic picture. So the idea of multiplier is basically, let's say you're minimizing this problem. This problem changes if you change x1, x2. This sort of becomes sort of larger and larger as you go this way. You draw your constraint now. What you do is you say, okay, whenever this sort of line touches the constraint, where does the gradient point? The gradient point this way. So it's perpendicular to the constraint. Now you're done. Right? So this is how you know this point is the optimal solution. Okay. So how do you describe this in, right? So how do you describe this in math, in algebraic equations is first, you compute this. Okay? First you compute this. Then let's look at when does this thing work, right? Let's say when does this thing work, okay? So Lagrangian multiplier is the idea that you can take a derivative of your function. Now let me also take a derivative of my constraint. Let me also take a derivative of my constraint. So what does the derivative of your constraint mean in this case? Well, the derivative of your constraint, of this linear constraint, is basically telling you which way, you know, how does this linear function change as a function x1, x2. Okay, so that's a derivative of your constraint. Okay, so if you think about this, let's say your constraint is 5 minus x1 minus x2. What this tells you is the sort of gradient of your constraint is minus x1 minus x2. Okay, so this is how the constraint now changes. Why is this thing important? Is because the gradient of this function is always perpendicular to the constraint itself. Right, this is perpendicular to the tangent, right? So the gradient of a function is perpendicular to the tangent line of the function. In this case, it's a linear constraint. The gradient is perpendicular to the line itself. Okay, so that's the whole thing we want to have in here. Okay, so let me say this sort of I guess slower in this is okay. So let's say you have a function, right? So what does the gradient mean? Is you can draw a tangent of the function, right? You can draw a tangent of the function. Your gradient is a perpendicular, there is a normal vector to the tangent of the function, right? Right. So you want your gradient to be perpendicular to the constraint. What we can do is basically for this constraint, you can take a derivative. The tangent to the constraint is this constraint function itself. This is a line, right? So to check whether your gradient is perpendicular to the constraint is equivalent to checking your gradient is parallel to the gradient of the constraint. That's mathematically how you check. Okay, so instead of, right, so I want perpendicular to the blue line. It's as equivalent to as I'm parallel to the normal of the blue line. To get the normal vector of the constraint, you can take this derivative. Okay, so the partial derivative is a normal that's perpendicular to the constraint itself. Okay, right. So that's the idea. So the whole thing goes like this. I want this to be, right, so I want this thing to make a right angle with my constraint. Okay, so that's what I want. Well, so we know the gradient of itself always is perpendicular, right? So what is perpendicular to the constraint? Well, the gradient of the constraint is always perpendicular to itself. So what do we want is, so we need this and to be parallel. Right? We need these two to be parallel to each other. Okay, so I want to be perpendicular to this thing. I know its own gradient is perpendicular to it. So I should be parallel to its gradient, such that I make the same angle to the constraint, right? Okay. How do you check if two vectors are parallel to each other? Right, so two vectors are parallel to each other if one is a scalar multiple of each other. Right, so that's how we check whether two things are parallel to each other. Right, so I have two vectors, right? So what does parallel mean? It means that they go in the same direction. The length may be different, right? So these two, for example, are perfectly parallel with each other. So this is true if there is a constant such that, let's say, this thing equal to lambda times this. This is if and only if, actually. This is if and only if. Okay, so algebraically, we define two things are parallel if I can find this constant such this is true. Right? So this is a definition of parallel things. Okay? All right, so now basically what you turn into is instead of checking whether this thing is equal to 0, what you check is you take this gradient, you take this gradient, you check whether I have this lambda that's equal to each other. Okay, this is what I need to check, right? Whether this lambda exists. This is the Lagrangian multiplier. Lagrange multiplier. Or in our case, this will be the price. Turns out this number that sits in front, this constant of proportionality is the price for our case. Okay, so we'll do the math and see this. But the whole idea is I need these two things to be parallel to each other because they're both perpendicular to the constraint. To be two things to be parallel, I need to find this constant, and that's how we need to solve this problem. Okay. So this is drawing for a better picture is at optimum. Which way do you go? You go, if you start here, you go inward. If you start here, you go this way. At this point, this gradient and this, for these two gradients are parallel to each other, both perpendicular to the constraint. Okay, so this is what must be happen at the optimal point. And now the math actually becomes quite simple. Now the math becomes very, very simple for us. How the math looks out is, so what happens at Lagrange multipliers, right? So at optimum, we need this thing plus lambda to be equal to 0, right? That's what I need. Okay, so now we can count the number of equations and solve the number of equations. Okay, let's look at how many equations we have. For this case, we have right, so this in the first coordinate has to be 0. In the second coordinate, only one. Right, so the second coordinate has to satisfy this equation. Okay, so now I have three variables. I have x1, lambda, x2, three variables, two equations. Can I get one more equation for this? Right, so if I have one more equation, I'll be done. I have three variables, three equations. I can solve the system equations. I'm done. Okay, right. So I have this comes from the fact that these two has to have a parallel. Can we get one more equation in this problem? Okay. The constraint itself, right? So the equation you have is the constraint itself, right? So the constraint itself says this thing has to be 0. So there's constraint itself. So here is how you get three variables, three equations. In our case, it turns out to be linear. So you just solve them and be done. You're done. You're finding out the right. You find out the ultimate solution. Okay, so this is three variables, three equations, and you're done. All right, so this, so now it's just a matter of solving the system equations, right? So for us, so what we have to remember is this is almost x1, x2, right? So your homework have more variables, but the exact same thing applies. Okay, it's just add more variables, it's just bigger system equation. Okay, so what do you get is right, so this is what always happens for us, right? So your system equations look something like this is your system equations for our type of problems. And why does the marginal cost has to be equal? Because they both equal to the same lambda. Okay, so that's why lambda is your price. Okay, so right, so what I claim is the price is right. So the price is the marginal cost of the function. Well, so this is your marginal cost. This thing equals to lambda. This thing equals to lambda. So they must have the same marginal cost. Okay, so what this implies. Okay, right. So it does not depend in the fact that the cost was quadratic, right? It doesn't depend on any of this. Right. So this is a natural consequence of the Lagrangian multiplier theorem, of the duality theorem. Right. So it says that if you're trying to supply a single load, it's the same type of good supplying a single load, the price at optimality is necessarily equal at every supply, at every producer. Okay. This is again, there's a much more powerful version of the theorem that applies to sort of more general context, but the idea is always the same. Right? So that's why for this kind of market, we describe a single price. Okay, because there is only one price, right? The marginal costs all equal to each other. This lambda is your price. Okay. Any question about that? Okay. Yes. Yes. Right. Yes. Right. Yes. That's true. Yes. Yeah. Also works. Also works. It works for a wider variety of situations. Very wide variety. So it works for. So basically, in general, what this works for is as long as your problem is convex, this thing applies. Right. So this is the version of a convex optimization problem. So really going to convexity theory, that's an entirely another entire class that's devoted to that. But this is a version of duality theory. And this works whenever the entire problem is convex. Here, certainly we have a convex optimization problem. And so the field of this type of analysis for duality really grew out of this observation, basically. So here, your constraint, the way you think about your constraint is basically the constraint shows up in this multiplier, right? So forms a constraint, but shows up in sort of your multiplier. And the way price happens, so this actually, you think about economic theory, right? Why must there be a price? There must be a price because the market is always constrained. Anytime you have constraints in a market, there will be a price, namely the Lagrangian multiplier associated with that constraint. Okay, so talk about sort of why does everything have to have a money sign? Why does everything value in terms of money and all that? But well, if you believe this theory, it sort of comes out of the math. You don't have a choice. You have to assign a price to it, right? And this tells you exactly what is the price to assign. There's sort of no arbitrariness to this problem. So that's why sort of this is the beauty of this theory, right? Why we like this theory. Okay. So later we'll see sort of when this thing can break down if sort of convexity is not met, and we'll see particular example of that. But for now, so remember this case when the theory works. Okay. Any other questions? Okay, so once you have this, solving the problem is sort of trivial at this point. you remember these equations, solving the problem is entirely trivial, mechanical at this point. So let's sort of do one example and solve the problem. Subtract 2, 5 minus x1 minus x2. So again, homework. The homework, you just have more numbers. The idea is the same. So you take a derivative x1, 0.5, x1 minus lambda equals 0, right? So this is your first condition. The second condition is 2x2 minus lambda equals 0. Okay, so 2n plus your constraint itself. Okay, so you apply those equations, you get this thing back. Okay? And then again to the system linear equations, whenever you do your homework, you do your exam, your job to get to this point, then it's okay to just show the solution. Right? It doesn't matter how you solve the system equations. So here, lambda is 2, x1 is 4, x2 is 1. So this is the problem we have. You can definitely have more, so you can definitely have sort of more variables. It sort of doesn't matter. Right? It's a bigger system. And this linear system is not very hard to solve anyways. Okay? So one note is we write L minus x1 minus 2 always. So the reason is for this constraint. There's two ways to write this. You can write this as x1 plus x minus L equals 0. We can write this as L minus x1 minus x2 equals 0. The conventions in power is you always have the load leading in front. Okay, this is just a convention. There's nothing too deep about this. But this will follow this convention, so your lambda turns out to be a positive number. You have to flip the sign later. Okay? So just whenever you write this equality, remember it's a constant, sorry, the load minus generation. That's just what we write. Okay? So again, once you have this, follow the procedure, things work out for the problem. Okay? Any questions for this? Okay, so one thing to remember is, so your computer doesn't solve the problem this way. So you can type this into a solver. There's many solvers will solve this problem. Your computer really doesn't solve it this way. Your computer does something else. So this is sort of conceptually how we think about it. In future homeworks, you'll be asked to explore how your computer might solve this thing. And how to recover this type of, and your computer may solve it. And then how do you recover this sort of lambda if you're actually a computer program solving this thing? Okay, so we'll do that later in class. But for now, the problem we do will be small enough. You can do it by hand to get to this stage. Then, you know, whatever you want to do to get the solution done. Okay. All right. So, any questions? Okay. So with that, let's end the class here today. The next class will continue, and then we'll look at what happens when we have inequality constraints instead of equality constraints.